Hi, so in this video I'm going to look at a quick algorithm, a Python script that essentially just does the algorithm of the sieve of Eratosthenes to leave all the prime numbers between 1 and a given number n. So the way the algorithm works, just in words, at first it generates all the numbers between 1 and a given number n, and it just removes. Okay, it doesn't even include the first one because it's not a prime number. So it ignores one. It generates all the numbers between 2 and a given number n. Then it assigns what I've called the anchor number. And the anchor number starts off as 2. And then, as you'll know from our previous video, you take 2 and then you square it. And then you remove it from the list. And then you add 2. So you add the anchor number to remove 6. Then you add the anchor number again to remove 8. And do it again and again and again and again and so on until you just remove all the multiples of 2. So you start by squaring the anchor number. The anchor number starts out as 2, and then you remove all the multiples of the anchor number by just adding on 2, right? Then it changes the anchor number to 3, and the anchor number is what I've called it in my script, you'll see that. And then it squares 3 and just removes that and then adds the anchor number on again. You see we've already removed 12, so it just does it again and removes 15, and then removes 18, it's already gone, 21 goes, 24, 27, 33 because 30 is already gone, and then removes 39, and then it'll remove 42, and then remove 45, and then that's it, because 51 is not in the list. Then it moves the anchor number along to 5, and it squares it to give you 25, and it removes that. Then it adds 5 to give you 30, which is already gone. Adds 5 again, 35 goes, 40 goes, 45 goes, 50 goes. Then it goes to 7, moves the anchor number to 7, squares 7, gives you 49, and it just removes it. Now we can stop here, and the reason we can stop here is because the sieve of Eratosthenes essentially just you only need the anchor number only needs to go as far as the square root of the upper bound is what I've called it. So like initially, before the program removes any numbers, it takes your upper bound, which in this case is 50, and it square roots it. So it takes the square root of 50, which is not a nice number, right? It takes the square root of 50, which is a little bit more than 7, right? And it essentially just rounds it up. So the square root of 50 to the nearest integer is 7, and then it adds 1, so it'll give you 8, right? So square root of 50 will be 7 point, I don't know what it is, right? 7 point something. And it'll round that to the nearest integer, which will be 7, and then it adds 1 to make sure that this number is included, so it gives you 8. And that tells you that the anchor number only needs to go as high as 8, so the anchor number is always less than or equal to 8. But because the number 8 is removed when we go through all the multiples of 2, it doesn't need to get to 8, it only needs to go as high as 7. And this is just what the program does in words. So if I go to the program itself, we'll just talk through it. So import math, it just imports everything you need. And then it assigns this number called the upper bound. I've called it the upper bound, which is essentially like something that the user can put in. So I've asked the user to enter a maximum number. And then it creates an array, a list of all the numbers between 2 and that upper bound. And the reason we've got this +1 on the end of the upper bound is so that you can include the upper bound, right? And then it just says for anchor, and anchor, remember, is that number whose multiples you're removing. That's what I've said here. Anchor is the number whose multiples you're removing. And it says for each anchor between 2 and the square root of so this is the integer square root of the upper bound, right? So the square root of the upper bound rounded to the nearest integer, +1 to make sure that we include the actual square root between the rounded and the one above. And then it says if the anchor's in the list, so if the anchor's in this whole list of numbers, then it takes what I've called the test number. And the test number is just whichever number you're on, right? So like initially we square 4 and that becomes our test number. Then we add 2 to give us our test number as 6, right? So test number is whichever number you're on. And initially the test is the anchor squared, right? We square the anchor. And then while the test is less than or equal to the upper bound, so we can't go higher than the upper bound, it's only everything up to the upper bound, if the test is in the list, then we get rid of it. If the test is in the list, then we get rid of it. Because if the test is in the list, that means it's a multiple of the anchor, which means it's not prime, so we can get rid of it. And then it adds anchor to the test. So the new test becomes the old test plus the anchor number. So initially, right, we started with 2, we squared it to remove 4, and then we added 2. We added the anchor, this number, to give us 6, right? And then when the anchor became 5, for example, we squared it to give us 25, and then we removed that. And then we added the anchor, which was 5. So we added 5 to give us 30, which was the next multiple of 5. And so that's what that final thing does. And it keeps doing it for all the anchor numbers between 2 and that integer square root of the upper bound plus 1. And then at the end, it just prints all of the numbers that are left in the list. So essentially, like, it works in the same way as the sieve of Eratosthenes. It takes all the numbers and then just removes a bunch. And then at the end, it gives you what's left. And what's left are the prime numbers. So if you were to run this, which I'll do now, you can see it asks you, please enter a maximum number. So we can put in like 1000, for example, and it just prints all the prime numbers like that. Obviously, it does it really fast, faster than we can do it. But yeah, I mean, if you want, you can check that these are all prime, but just believe me, they're all prime. And we can run it again, and like, and I can put in like 5, for example, and it'll give me 2, 3, and 5. So it's inclusive, it'll give me 5 as well. And if you're curious what happens when you put in a negative number, it doesn't make any sense to it. And if you put in 1, it'd just be the empty set because there's nothing there. There's no prime numbers between 2 and 1, right? And then if you were to do it with some, decimal number like this, it doesn't make any sense either. So it has to put in an integer for it to make any sense. It has to be a positive integer for it to make any sense. But this is essentially just a short program that does the sieve of Eratosthenes for you. So yeah, there you go. And you can put in as high a number as you like. So you can put in like, I put in 1,000,000 there. This will take a while, and it's still going because it hasn't given me these 3 arrows or whatever here. But eventually this will print all the prime numbers between 2 and 1,000,000. But there you go. Thanks for watching, and remember, maths is the way.